Double-click a piece of modern malware, and the binary immediately initiates a high-speed assessment of its memory space. It begins an aggressive scan of its surroundings to identify any sign of observation. Reverse engineering these binaries is a hostile cat-and-mouse pursuit. The analyst tries to dissect the code, while the code executes logic specifically designed to hide its true purpose. Observation is not enough. To map the malware's behavior and survive its execution lifecycle, the analyst must actively feed the code false information at every step. The first line of defense triggers within milliseconds of launch. The malware queries the process environment block, a user mode structure known as the PEB, searching for any attached debugging tools. As shown in this C implementation, the malware calls isDebuggerPresent, reading the being debugged flag at offset 0x02. If 1, it detects a debugger. To bypass this, the analyst manually sets the EAX register to 0, spoofing a clean environment. Advanced samples don't rely on simple flags. They measure time to sense if an analyst is single-stepping through instructions. Native execution completes in nanoseconds. However, when an analyst pauses the code to examine a function, the cycle count jumps into the milliseconds. The malware uses the RDTSC instruction to detect this discrepancy. If the count exceeds a threshold, the malware terminates. Analysts counter this by using plugins like Silahide. These tools hook into the timing APIs and forge the CPU cycle counts, feeding the malware false metrics that simulate native speed. Defeating these tripwires requires perfect environmental deception. If a single check fails, the sample will quietly exit before revealing its malicious payload. Once the code confirms no debugger is attached, it transitions to a broader environmental survey. It begins interrogating the machine's configuration to determine if it is running on a physical host. The binary queries the CPU ID instruction to look for a hypervisor bit, and scans the network adapter's MAC address for registered prefixes assigned to VMware or VirtualBox. This phase is a hostile radar sweep, scanning the hardware and registry keys for any indicators of a virtualized analysis environment. It also monitors for behavioral artifacts. The code may measure mouse movements over a 2-minute window to verify that a real human is interacting with the desktop. Bypassing debugger checks is useless if the operating system lacks human history. To move forward, analysts must populate the VM with documents, browser history, and realistic software to make the environment look lived in. This matrix of x86 instructions illustrates code misdirection, the practice of twisting the binary's architecture to break the automated tools an analyst relies on. One method is the opaque predicate. The malware inserts conditional jumps where the outcome is mathematically predetermined, but the disassembler cannot prove it. This forces analysis software to map out massive, fake execution paths that lead to dead ends. Overlapping instructions exploit the variable length of x86 opcodes. By jumping into the middle of a multi-byte sequence, the malware forces the disassembler to misinterpret the subsequent bytes, turning valid code into a stream of garbage instructions. The malware can also hide its logic in thread local storage callbacks. These TLS functions execute their defensive checks before the program's original entry point is even reached, often before the debugger can set its first breakpoint. Because static analysis tools rely on structural logic, they are vulnerable to these architectural traps. The analyst must manually intervene, patching out junk instructions to reveal the true path. Navigating these layers leads to the primary target, the configuration block containing the command and control domains and the encryption keys used for exfiltration. Advanced malware protects this sensitive data using a rolling XOR scheme. It cycles a multi-byte key over the configuration block, ensuring the payload remains unreadable until the moment it is needed in memory. Sophisticated frameworks often conceal these encrypted blobs deep within the binary's dormant resource sections, disguised as icons or benign application data. Analysts use specialized tools to identify the decryption routine and carve out these strings directly. This allows them to identify the attacker's infrastructure without risking a full detonation of the sample. Safely extracting this embedded data is the only way to build effective network-level defenses before the malware reaches its final stage of execution. Even after the code is unpacked, the malware has one final defensive layer to prevent the analyst from saving a clean copy of the payload to disk. It utilizes header erasure. The malware zeroes out its own PE header in memory. If an analyst tries to dump the process for later study, the missing header prevents standard reconstruction tools from rebuilding the file. Most evasive of all is a technique known as process ghosting. The malware marks a file for deletion using an NTFS delete pending state. It maps the malicious payload into memory from that file and then lets the operating system delete the physical source. This allows the malicious code to execute purely from RAM, while the physical file on disk ceases to exist. Any antivirus scan of the hard drive will return a clean result. Defeating self-defending malware is a test of architectural mastery. You have to anticipate its logic, disarm its traps, and outmaneuver its environmental checks. Success proves that the analyst, not the code, ultimately controls the machine.